All right, working a little bit more at the top 100. Threesome. Given an integer array nums, sorry, return all of the triplets nums I, j, k such that I does not equal j, I does not equal k, and j does not equal k, which is the fancy way of saying that none of them are the same. Um, and nums I plus nums j plus k equals 0. Note that the solution set must not contain duplicate triplets. So in this one right here, there's two sets of 3 that will add up to 0, and that's negative 1, 1, and 0. Yeah. All right. So, intuitively, you'd think, well, you could just iterate, you could just have a loop. We'll have a triple nested loop. And that triple nested loop would go through all of them. So you set the first pointer and then you go through all the rest of the options. And that would work, but it would be really slow. I'm going to start commenting a little bit better. So the problem is that if if it's a triple nested loop, you get O n to the third, which is really bad. We don't want that. What do we do instead? How do we avoid comparing all of them? Now, I did get some comments saying that for twosome, their solutions involved like hash maps and then figuring out basically the complement to each number. And I think that's good, but for this one, I think we can do something different that'll also work fast. Because for this one, the tricky thing is that you had to compare 3 values. So even if you take 1 and find the complement, you had to find the 2 that add up to that complement. So what can we do? How can we skip some steps? I think that we can use a 2-pointer solution. 2-pointer solutions are great. Basically, they just allow you to iterate through 2 different numbers, but with specific criteria to adjust the proper pointer so that you only compare the values that matter. So what do we do? First, I want to make this a little bit easier on us. We know that this is going to take a while because our intuition was ON3. So I don't think it's really going to cost us anything to sort it. Okay? Because now we can derive much more information from the array at any state in time. Because rather than having to compare all the values, since we sort it, once we start getting to values that are like, say, too big to add up to 0, we can lop that off. So here's my idea. Basically, once we sort it, what we can do, because you can notice there's a little bit of like symmetry almost. Since you had to add it up to 0, you know that for every digit you go up, you had to bring one down. So basically, we could have a 2-pointer approach where we iterate one number, but for the remaining 2 numbers, we kind of collapse in. Okay? Meaning, so let's say we have like -4, and then we have like 1 and 3, 1, 2, 3, or we could do like 1, 2, 2, 3. So we start by having this be, but we have the first pointer be just a simple iterator. And that's going to go from -4, then 1, then 2, then 3, then 2, then 2, then 3. -4, and then we're going to set 2 pointers. And they're going to start at the left and right ends of the remaining array. And then they're going to converge. So they're going to work their way in. So because we know that the left number is going to be greater than or less than the right number. So if we add the left and the right number and it's too small, then we just tick the left number up. And if we add the left and right number and it's too big, then we take the right number down. And then through this process, we're skipping so many comparisons because we're only comparing, like, you know, we're only going in a direction that we know could be going the right way. Instead of doing all the comparisons where we modified this iteration to use 2 pointers, and the 2 pointers dynamically approach the right solutions. Okay. Okay, now we're gonna I'm learning through LeetCode that 2-pointer solutions are very useful. And it makes sense because it basically takes what would be 2 different loops and you apply the criteria depending on what kind of problem is, and you can turn 2 loops into 1 loop. So keep that in mind. So we're going to say for I in range, it would be length of nums -3. Or sorry, -2, because it's not inclusive. And since we are comparing at least 3 numbers, and we know that I is going to be the first one, we don't need to ever have I be one of the last 2, because there wouldn't be 2 numbers left to compare I to. Okay? We are going to have to consider duplicates. We'll do that right here. The way that we'll consider duplicates is to, I'm pretty sure it'll just be checking if we've checked this I before. Like, because the only way that there could be a duplicate set, actually, is if you have something like -2, no, -1, no. Like -1, -1, 0, 1. So through this approach, we'd say, okay, -1 is the first pointer. Okay, now we see that we can take -1 plus, okay, we converge these and we find that 0 plus 1 plus -1 equals 0. Okay, awesome. So we're done with that one. Now we iterate to this one and we get the exact same solution. So I think that we just need to make sure that that first pointer is never the same as one that we've checked before. And since it's now sorted, we can just check to make sure it's not the same as the last one. So we're going to check to make sure that it's not the first number in the list. Because if it's the first number list, it can't have a prior one. And now we're seeing if it's the same as the number beforehand. So that will make sure, and then we do continue. Continue is the keyword to skip this iteration of the loop. So we're saying, hey, so if we've already seen this number before as the first number of the possible triplet, we don't need to do it again, because we will, if we got any matches with a prior number, we're just going to get duplicates now. Because the same number, and it's sorted. I hope that makes sense. Let me know if it doesn't. Well, now we just need to do 2 pointers, and yeah, we just need to do the algorithm that I described. Set left and right pointer and converge them. So the left L is going to be I plus 1. Okay, and then R is going to be length of nums minus 1. So those are the 2 extrema in the remaining list. And we're going to tick up L, and we're going to tick down R. Because L is always going to be less than R. So we know, this is the key part of it, is what we can deduce on every iteration. We know that if I plus L plus R, or the indices, where those indices are, is bigger than 0, then we're not going to get any closer to 0 unless we tick down R, because we can't tick down L, because L is set to the minimum possible value. Yeah, okay, I think I've described it pretty well. And I think it's actually pretty straightforward. Yeah. So let's get the sum of these 3 values, and then we figure it out from there. Sum is already a keyword. We'll just use S. Sum equals nums I plus, no, actually we can just say nums I plus nums L plus nums R. Okay? So now we know if it's too big, which is it's greater than 0. Oh, wait, sorry. We need to put this in a loop, because we need to iterate through these 2 pointers. So we're actually going to do a while loop. Okay, that's the 2-pointer thing. Once they cross or become the same value, then this will no longer be true. Okay, so while L is greater than R, S is greater, there we go. If S is greater than 0, that means it's too big, and we have to tick down the R. If it's less than 0, that means it's too small, and we need to tick up the lower bound. Otherwise, that means it equals 0, and we can just append that to the triplets. There we go. All right. I think that's everything. Time limit exceeded. Oh, yep. Sorry. Once we find a triplet, we never adjust the L and R value, which means that this will just keep looping over and over because L and R are never adjusted. So, if we find a triplet, we can tick up L and we can tick down R at the same time. Here's why. If ticking up L but not ticking down R was still 0, it would be a duplicate, because the only way that L could be different but R is not is if the two L indices were the same value. Meaning that there's no possible way to change one but not the other and have it either be 0 while not being a duplicate. It's just not going to happen. Awesome. And we run it. Wrong answer. Okay, we got one duplicate. Okay. So it looks like we dealt with duplicates for I, but not for L and R. That makes sense. So we know that the first number in both of them is -2. So we can just run through that pretty quick. We check the sum. So we have 0 and 2. Oh, interesting. That's weird. So if you can't see what's going on, basically when we get a duplicate just based on circumstance. So we up L and we subtract R, but that's still 0 and 2. Do we just check to make sure it's not already in there? Would this take too long? So is that it? I guess I should have just ran it. Time limit exceeded. That's a big list. Does it work for case 4? It does work for case 4. Awesome. Oh my goodness, that's a big list. So let's see if it gets past the sort. Because if it doesn't get past the sort, that's going to be a big problem. it suddenly worked. Do I just need to keep resubmitting until it gets lucky? Okay, so it didn't work, but it works here. Y'all seeing this? It works here, but not there. I'm just gonna try resubmitting until it works. Does this not, does the run thing not consider the time limit? All right, I had to take a little pause for a second, um, and yeah, look some things up. But yeah, there's one tiny little optimization that we could make to make this work a lot faster. Just the smidge faster. I think it's just that smidge. Because remember, we were only missing 2 test cases for time. But this should work a lot faster. Basically, so we append the triplets right away, and then basically tick up L and R as much as we can. So skipping past all the duplicates. Instead of checking if it's already in there, which would take a while on big lists, because we'd have to iterate through. Actually, well, yeah, if we're starting to get big accumulation of triplets, it's going to take a while. The more triplets that we add, we had to check that there's not already a duplicate in there. Instead, we just skip through that process by making sure it never happens, by changing the 2 pointers, skip by basically getting to the point where the 2 pointers go past all the duplicate values. In a very similar way that we do this, we just loop that until, yeah, I think that makes sense. All right. Yeah, sorry I had to take a little pause there. But yeah, I was just getting a little frustrated because I was so close. But yeah, there's another one.